This video will still focus on worksheet number 2, and it will go over 11, 17, 18, and 20. So number 11, what force is necessary to accelerate a 5 kilogram mass to 10 meters per second in 5 seconds? So if we set this up like normal, F equals m 5 times a. Do we have a? No. This is a velocity. This is a time. So we need to do something before we can start solving for force. We need to find acceleration. The acceleration is velocity over time. We know that the acceleration is 2 meters per second squared. We'll plug that in. The force is 10 newtons. Not that complicated. Because we just need to recognize when we are given a velocity versus an acceleration. Number 17, we've got a 4 kilogram mass sitting on a table with 5 newtons of friction and a 25 newton force. How fast is it going to accelerate? So we know we're going to be doing F equals m times a. We know that the mass is 4 kilograms. We're finding acceleration. How much force do we have? Does the 25 newtons get entirely transferred to the object? Not entirely, because it first has to overcome friction. So it's going to be 25 minus 5, which is 20. So 20 equals 4 times the acceleration. Divide both sides by 4, divide both sides by 4, and we are left with an acceleration of 5 meters per second squared. If instead that 25 newtons did not have to first deal with friction, that object would be going faster. It would be going nearly 6 meters per second squared. Number 18, how much force is required to accelerate an 8 kilogram mass at 5 meters per second if there's 14 newtons of friction? Okay, so let's think about this. Let's just find the force to accelerate that mass regardless of friction. Force equals mass times acceleration. So it's going to take 40 newtons of force. But there's also 14 newtons of friction. So we need to also plus account for friction. So that's going to leave us with 54 newtons of force. Because if we just gave this object 40 newtons of push, right? We give it 40 newtons. We need to subtract the 14 newtons of friction out of there, which means that we're left with 26 newtons actually being applied to the box after accounting for friction. If we then divide 26 by 8, we're left with something around 3.3-ish, right? The problem with that is 3.3 is not 5 meters per second squared, so we did something wrong. We need to account for this, which means that the total push that we need to give has to be 14 newtons bigger. So it can't be 40, it has to be 54 to end up being 40 newtons applied to the 8 kilogram object, which accelerates to 5 meters per second squared. So we need to add on that friction to account for it. One of my favorite sets of problems are these ones with the hanging object. So what we've got here is we've got a table. We're assuming that this table is frictionless. There's no friction between the table and this block. Is that real? No, of course not. If we're looking at this here then, what is the only force acting on these two blocks? Well, the only force, since we're not pushing it in this direction, we're not pulling the string in that direction or anything like that, the only force that we see is gravity. Force of gravity pulling down a 5 kilogram block. If force of gravity is just mass times the acceleration due to gravity, 10, we know that the force of gravity is pulling in that block with 50 newtons. If there's 50 newtons tugging on that block, and this block is attached by a string through this pulley to this block, we know that there's 50 newtons pulling on this one, and therefore there's 50 newtons pulling on this one. We can then figure out how fast that 20 kilogram object will accelerate by taking 50 newtons equals 20 times A. Divide by 20, divide by 20, and we are left with 2.5.